Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 400, titled Nth Digit. Together, we'll explore how to determine the nth digit in an infinite integer sequence, breaking it into manageable steps with an efficient approach. Let's dive in. In this problem, we are tasked with finding the nth digit in an infinite sequence of integers written consecutively. The sequence starts from the number 1 and continues indefinitely, with each number directly following the previous one without any spaces. For example, the sequence begins as 1 2 3 4 5 6 7 8 9 1 0 1 1 1 2 and so on. The challenge is to determine the specific digit at the position n in this unending sequence. The input to the problem is a single integer n, where n represents the position in the sequence, and n can range from 1 to 2 billion. The output is the digit found at that nth position in the sequence. This means that our solution must efficiently locate and extract the digit at the specified position, even for very large values of n. To help clarify the problem, let's look at some examples. In the first example, the input n is 3. The sequence begins as 1 2 3 4 5 6 7 8 9 1 0, and if we count, we see that the third digit in this sequence is the number 3. Therefore, the output in this case is simply 3. In the second example, the input n is 11. Counting through the sequence, we find that the 11th digit is the first digit of the number 10, which is 0. Hence, the output for this example is 0. These examples illustrate how the position n maps to a specific digit within the concatenated sequence. Now consider another example where n is 15. If we count through the sequence 1 2 3 4 5 6 7 8 9 1 0 1 1 1 2, we see that the 15th digit is the first digit of the number 12, which is 2. So, the output here is 2. These examples highlight a few key scenarios. N could correspond to a digit within a single-digit number, such as in the first example, or within a multi-digit number, such as in the second and third examples. Additionally, the constraints of the problem specify that n can be as large as 2 billion, meaning our solution must handle both small and large values of n efficiently. To design an efficient solution, we need to consider the structure of the infinite sequence. The sequence grows in length as numbers with more digits are added. For instance, there are 9 single-digit numbers contributing a total of 9 digits, 92-digit numbers contributing 180 digits, and 903-digit numbers contributing 2,700 digits. Identifying the range where n falls is critical for narrowing down the search space. We also need to handle edge cases, such as very small values of n, like n equals 1, where the output is simply 1, and values of n that lie at the transition points between numbers of different digit lengths, such as n equals 10 or 11. For very large values of n, close to the upper limit of 2 billion, our approach must be optimized to avoid excessive computation while accurately determining the target digit. To solve the problem of finding the nth digit in the infinite sequence of integers, it's important to first consider different approaches that we might take. One option is the brute force approach, where we generate the sequence by concatenating integers starting from 1 and continue doing so until the length of the sequence exceeds n. Once we have the sequence, we can directly access the nth digit. While this method is simple and intuitive, it has significant drawbacks. The repeated string concatenation makes it computationally expensive, with a time complexity of n squared, and it also consumes a large amount of memory, making it impractical for large values of n, such as 10 to the power of 9. A more promising direction is the optimized mathematical approach. Here, instead of explicitly generating the sequence, we use mathematical insights to determine the range and position of the nth digit. This approach takes advantage of the fact that numbers in the sequence contribute digits in predictable groupings, such as 1-digit numbers from 1 to 9, 2-digit numbers from 10 to 99, and so on. By calculating how many digits each group contributes, we can narrow down the range where the nth digit lies, without constructing the entire sequence. Once we've determined the range of numbers containing the nth digit, we can pinpoint the exact number and the digit's position within that number. To do this, we start with the smallest group, the 1-digit numbers, and iteratively subtract their total contribution to the sequence from n. We move through groups of increasing digit lengths, 2-digit, 3-digit, and so on until the remaining value of n falls within the current group. At this point, we know the exact range of numbers to focus on. From there, we calculate the specific number in that range by dividing n by the digit length and locate the exact digit within that number. This method is highly efficient, with a time complexity of O log en, because the number of groups is logarithmic with respect to n. This efficiency, combined with minimal memory usage, makes the optimized approach scalable to very large inputs. While we also considered a hybrid approach, using brute force for small values of n and switching to the mathematical method for large n, it was deemed unnecessary. The optimized approach alone is sufficient, as it handles all cases efficiently without adding extra complexity. When comparing these approaches, the trade-offs become clear. The brute force method, while simple to implement, is computationally inefficient and unsuitable for large values of n due to its excessive memory and time requirements. The hybrid approach, while potentially useful for balancing simplicity and scalability, introduces unnecessary complexity and redundancy given how well the optimized mathematical approach performs across all input sizes. The optimized approach strikes the ideal balance of simplicity, efficiency, and scalability. Its mathematical foundation allows us to directly leverage the structured pattern of the sequence, eliminating the need for explicit sequence generation. This makes it both space and time efficient, fulfilling the problem's requirements effectively. Ultimately, the mathematical insights gained from understanding the sequence's structure offer a robust and elegant solution, making this strategy the clear choice for tackling the problem. To solve the problem of finding the nth digit in the infinite sequence of concatenated positive integers, we first need to understand the structure of the sequence. The sequence starts with one-digit numbers from 1 to 9, contributing 9 digits in total. Then, we have two-digit numbers starting from 10 to 99, contributing 180 digits. Next, three-digit numbers from 100 to 999 add 2,700 digits, and so on. The key insight here is that the nth digit must belong to a specific block of numbers, grouped by their digit length. Our goal is to identify the block that contains this digit and narrow it down further to find the exact number in digit. We start by initializing the block's digit length to 1 and the count of numbers in the block to 9. As long as n is greater than the total number of digits in the current block, we reduce n by the total digits in that block and move to the next block by increasing the digit length and the count of numbers appropriately. This step-by-step reduction allows us to pinpoint the block where the nth digit lies. As we move through the blocks, the count of numbers in each block increases tenfold for every increment in digit length, progressing from 9 to 90, then to 900, and so on. Once we identify the block where the nth digit resides, the value of n will now represent its position within this block, rather than the entire sequence. At this point, we calculate the starting number of the block, which is determined by the formula 10 raised to the power of the digit length minus 1. For instance, the block of three-digit numbers begins at 100. Next, we compute the offset within the block by dividing the adjusted n-1 by the digit length. Adding this offset to the starting number gives us the exact number that contains the nth digit. This process allows us to efficiently locate the specific number without having to generate the entire sequence up to n. With the target number identified, the next step is to extract the specific digit. First, we determine the position of the digit within this number by finding the remainder when the adjusted n-1 is divided by the digit length. Then, we convert the number into a string, which allows us to directly access the digit at the calculated position. This digit is our final result. Through this mathematical approach, we avoid the computationally expensive task of explicitly constructing the sequence. The algorithm's efficiency stems from its ability to narrow the search space logarithmically, as the size of each block grows exponentially with the digit length. This makes the solution both time and space efficient, with a time complexity of O log n and a constant space complexity. By utilizing integers and strings only for intermediate calculations, the algorithm handles even large values of n seamlessly. Let's apply this method to an example where n equals 15. We start with one-digit numbers, which contribute 9 digits. Since n is greater than 9, we subtract 9 from n, leaving us with 6. Now, we move to two-digit numbers. The total digits in this block are 180, and since n is less than 180, we determine that the nth digit lies in this block. The starting number for two-digit numbers is 10, and the offset within the block is calculated as 6 to 1, divided by 2, which equals 2. Adding this offset to the starting number gives us 12. To extract the specific digit, we calculate the digit index as 6 to 1 modulo 2, which equals 1. Converting the number 12 to a string, we find the digit at index 1 is 2. Therefore, the output is 2. This example highlights the efficiency of the approach, as it narrows down the solution without generating the full sequence. Now let's consolidate this process into code. The implementation begins by initializing the digit length as 1 and the count of numbers in the block is 9. Using a while loop, we reduce n by the total digits in each block until n fits within the current block. Then, we calculate the starting number of the block using the formula 10 raised to the power of the digit length minus 1. The offset within the block is determined by integer division of n minus 1 by the digit length, which gives us the target number. Finally, we calculate the digit index within this number, convert the number to a string, and return the digit at the index. This Python function encapsulates the entire algorithm and can handle both small and large values of n efficiently. For instance, calling the function with n equal to 15 returns the digit 2, demonstrating correctness and clarity in the implementation. This solution calculates the nth digit in a sequence of concatenated integers. The problem involves determining the range, specific number, and the exact digit within that number. 1. Step 1. Start by identifying the digit length of the number containing the nth digit. Initially, digit underscore length is 1 for one-digit numbers, and count is 9, numbers 1 to 9. The code iterates through increasing digit lengths, e.g., 2-digit, 3-digit, until we locate the range where the nth digit lies. For each digit length, the total number of digits in that range is computed as digit underscore length asterisk count, and n is reduced accordingly. 2. Step 2. After determining the digit length, calculate the starting number of the range using 10 caret digit underscore length 1, e.g., 10 for 2-digit numbers. The exact number containing the nth digit is found by adding n1 / digit underscore length to the start. 3. Step 3. Within this number, the nth digit's position is n1% digit underscore length. Convert the number to a string and extract the required digit at this position. Return it as an integer. The algorithm is efficient, as it avoids constructing the massive concatenated sequence directly. The time complexity is O log n, where n determines how many digit ranges need to be processed. This ensures the solution is scalable for large values of n. This is the complete Java implementation of LeetCode problem number 400, nth digit. The logic mirrors the Python implementation provided, with adjustments for Java-specific syntax, such as type declarations, the use of math.pow for exponentiation, and character.getNumeric value for extracting a digit from a string. The implementation follows the same three-step approach: determining the range of digit lengths, identifying the number containing the desired digit, and finally extracting the specific digit. This ensures efficient computation without iterating through all digits explicitly. To solve this problem, we start by determining the digit length of the number that contains the 11th digit. Initially, the digit length is set to 1, which corresponds to single-digit numbers, and the count of numbers in this range is 9. We check if 11 is greater than the total number of digits in this range, which is 1 times 9, or 9. Since 11 is greater than 9, we subtract 9 from 11, leaving us with 2. Then, we move to the next digit length, which is 2, representing 2-digit numbers, and the count here becomes 90. Now that we know the digit length, the next step is to find the number that contains the second digit in this range. The range for 2-digit numbers starts at 10, so we calculate the number using the formula start plus the integer division of n1 by the digit length. Substituting the values, we get 10 plus 2 to 1 divided by 2, which equals 10. Finally, we determine the specific digit within this number. Using the formula for the digit index, we calculate n1 modulo the digit length. Here, 2 to 1 modulo 2 equals 1. Converting the number 10 to a string, we access the digit at index 1, which is 0. Therefore, the output is 0. For the next example, we want to find the 15th digit. We begin by determining the digit length of the number containing this digit. Starting with a digit length of 1 and a count of 9, we calculate the total digits in this range as 1 times 9, which equals 9. Since 15 is greater than 9, we subtract 9 from 15, leaving us with 6. We then move to the next range with a digit length of 2 and a count of 90, representing 2-digit numbers. Now that we know the digit length, we find the actual number that contains the 6th digit in this range. The range for 2-digit numbers begins at 10. Using the formula for the number, we calculate 10 plus 6 to 1 divided by 2, which equals 12. Finally, we determine the specific digit within this number. The digit index is found by calculating n1 modulo the digit length. Substituting the values, we get 6 to 1 modulo 2, which equals 0. Converting the number 12 to a string, we access the digit at index 0, which is 1. Thus, the output is 1. Now, let's consider the 190th digit. We start by determining the digit length of the number containing this digit. Initially, the digit length is 1, and the count is 9, representing single-digit numbers. The total digits in this range are 1 times 9, which equals 9. Since 190 is greater than 9, we subtract 9 from 190, leaving us with 181. Moving to the next range with a digit length of 2 and a count of 90, we calculate the total digits in this range as 2 times 90, or 180. Since 181 is still greater than 180, we subtract 180 from 181, leaving us with 1. Now, the digit length becomes 3, and the count is 900, representing 3-digit numbers. With the digit length determined, we calculate the number that contains the first digit in this range. The range for 3-digit numbers starts at 100, so using the formula for the number, we calculate 100 plus 1 to 1, divided by 3, which equals 100. Finally, we find the specific digit within this number. The digit index is calculated as n1 modulo the digit length. Here, 1 to 1 modulo 3 equals 0. Converting the number 100 to a string, we access the digit at index 0, which is 1. Therefore, the output is 1. In analyzing the time complexity of the solution to problem number 400, we start by understanding how the algorithm determines the nth digit step by step. First, we identify the range in which the nth digit lies. This is done using a while loop that iterates through digit ranges, such as 1-digit numbers, 2-digit numbers, and so on. During each iteration, the algorithm reduces the value of n by the product of the current range's digit length and the count of numbers in that range. For example, there are 9 1-digit numbers, 92 digit numbers, 903 digit numbers, and so forth. The number of iterations in this loop is proportional to the number of digit ranges, which grows logarithmically with n. Therefore, this step has a time complexity of O log 10 n. Once the range is identified, the next step is to determine the specific number within that range. Calculating the starting value of the range, such as 10 for 2-digit numbers, is done in constant time, as are the arithmetic operations to find which number corresponds to the reduced value of n. These operations are all O(1). After identifying the specific number, the algorithm determines the exact digit within that number. This is done by converting the number to a string and indexing into it to extract the desired digit. The time complexity of this step depends on the number of digits in the number, which is equal to the current digit length. Since the digit length grows logarithmically with n, this step has a time complexity of O log 10 n. Combining all steps, the most time-consuming operation is the while loop used to determine the range of the nth digit, which runs in O log 10 n. Both the number identification and digit extraction steps are either O(1) or O log 10 n at most. Therefore, the overall time complexity of the solution is O log 10 n. This logarithmic time complexity highlights the efficiency of the approach, especially in comparison to more naive solutions. Now, let's examine the space complexity of the algorithm. The solution uses a constant number of variables, such as digit underscore length, count, start, number, and digit underscore index. These are all scalar values that require O(1) space. The only additional memory usage comes from the temporary conversion of the number to a string when extracting the specific digit. The size of this string is proportional to the number of digits in the number, which is at most logarithmic in n. Therefore, the memory required for this step is O log 10 n. Since the algorithm does not use any additional data structures or recursion, the overall space complexity is dominated by the string conversion and is therefore O log 10 n. This space efficiency ensures that the solution remains scalable even for very large values of n. To put this into perspective, consider the brute force approach to solving the problem. A naive method would involve generating all numbers sequentially from 1, converting each to a string, and concatenating them to form a single sequence. To find the nth digit, you would simply index into the sequence. However, this approach involves generating and concatenating numbers up to n, resulting in a time complexity of O n. Additionally, the memory required to store the concatenated sequence would also grow linearly with n, leading to a space complexity of O n. In contrast, the optimized solution avoids explicitly constructing the sequence of numbers. By narrowing down the range mathematically and directly calculating the target digit, it achieves a time complexity of O log 10 n and a space complexity of O log 10 n. This mathematical efficiency makes the optimized solution far superior to the brute force approach, especially for large inputs. The logarithmic time complexity of the optimized solution can be explained mathematically. The algorithm iterates over digit ranges, where the size of each range grows exponentially. For instance, there are 9 one-digit numbers, 92 digit numbers, and 903 digit numbers. This exponential growth limits the number of ranges the algorithm needs to process, resulting in O log 10 n iterations. Similarly, the space complexity is dominated by the temporary string conversion, which depends on the number of digits in the number and is proportional to log 10 n. When analyzing best, average, and worst-case scenarios, the time and space complexities remain consistent at O log 10 n, because the digit range calculation process is always logarithmic. This consistency and efficiency make the optimized solution well-suited for handling very large values of n, providing a significant improvement over the brute force method in both time and space requirements. One of the most common mistakes when solving the nth digit problem is misunderstanding the sequence itself. Instead of treating it as a continuous concatenation like 123,456, some assume it's made up of individual numbers such as 1, 2, 3. This leads to incorrect indexing and flawed logic for identifying digits. Another frequent pitfall is mismanaging digit ranges. For example, many people overlook that two-digit numbers, from 10 to 99, contribute 180 digits to the sequence because each number adds 2 digits. This can result in errors when calculating where the desired digit falls. Off-by-one errors are another source of mistakes, especially when transitioning between ranges or using zero-based indexing. For instance, forgetting to adjust by subtracting 1 when pinpointing the exact digit within a number can throw off the entire solution. Finally, relying on a brute force approach, where you concatenate numbers until the sequence reaches the desired length, might seem straightforward but becomes impractical as n grows. This method consumes excessive time and memory, making it unsuitable for larger inputs or competitive coding scenarios. Skipping edge cases is a critical issue to watch out for. For instance, when n corresponds to the very first digit of a new range, such as n equals 10 or n equals 190, it's easy to miscalculate the transition and return the wrong result. Similarly, solutions often fail under very large values of n if they aren't optimized. To solve this problem efficiently, it's important to recognize patterns within the sequence. The sequence is structured in digit-based ranges, single-digit numbers from 1 to 9, two-digit numbers from 10 to 99, three-digit numbers from 100 to 999, and so on. Instead of generating the full sequence, you can identify the range where n lies, locate the specific number within that range, and extract the correct digit. This method avoids unnecessary computations. You should also focus on achieving a logarithmic time complexity, ideally O log n, by systematically narrowing down the range and using arithmetic calculations. Lastly, adopting a modular approach, breaking the task into smaller, manageable steps like locating the range, identifying the number, and extracting the digit makes the solution easier to implement, debug, and explain during interviews. The nth digit problem has some interesting connections to other problems on LeetCode. For instance, while this problem specifically focuses on finding the nth digit in a concatenated sequence, problems like LeetCode 44, wildcard matching share a similar need for precise indexing and careful handling of edge cases. Another related challenge is LeetCode 7, reverse integer. Although the context is different, it also involves manipulating digits and addressing edge cases, especially when dealing with integer boundaries. LeetCode 43, multiply strings is another example where digits are treated as strings, requiring efficient computation and careful handling of large inputs. These problems, while unique in their own right, all emphasize the importance of digit manipulation, modular problem solving, and edge case awareness, making them great practice if you're preparing for interviews or aiming to strengthen your skills in this area. There are several approaches to solving the nth digit problem, each with its own trade-offs. The brute force approach involves directly concatenating numbers until the length of the sequence exceeds n. While this is simple to implement, it's incredibly inefficient for large values of n due to high time and space complexity. This method is generally not practical for competitive programming or interviews. A more efficient approach is to use mathematics to identify the range where the digit lies, locate the specific number, and extract the digit. This avoids generating the sequence entirely, significantly improving performance. However, it requires a strong grasp of arithmetic calculations to avoid off-by-one errors. For the most optimized solutions, binary search can be employed to locate the range where n falls, particularly useful for extremely large constraints. While this approach minimizes computations even further, it comes at the cost of increased implementation complexity. Depending on the problem constraints, you can choose the method that best balances simplicity and efficiency for your needs. Great job! To summarize, we solved the nth digit problem by breaking it into smaller steps, analyzing patterns in the sequence, and optimizing for time and space. This approach is a valuable technique for solving similar numerical problems. Thanks for watching, and be sure to check out more coding tutorials on our channel. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!